Alright, I've had a bit of a request to go through voltage and power in series and parallel circuits and how it works. So, let's do this thing.
Ready?
Alright, so let's begin here. So let's say I've got some circuit with, let's give it 10 volts, 10 volt power supply and a 5 ohm resistor. Well, we've got the circuit, it's a complete circuit, everything's connected, there's 5 ohms in the circuit. Couple of key points. Let's look at this. I have drawn here what's called a cell. I could easily have drawn a battery. And a battery is just drawn as a cell with a dotted line going to another cell. This really represents the idea that there's many cells stacked together. Another type of power supply I could have, of course, is something generated, say, by a power pack, something that's plugged into the wall. We just represent that as 2 dots with the lines coming from them. So I've drawn that down there as well so you can see how it looks. You've probably already seen that when you're dealing with, say, alternating current. The difference between alternating current and direct current is alternating current has a little alternating line on it. If we get rid of the alternating line, it's direct current. So there we go, we have our power supply and we have a load. We have a 5 ohm resistor in our circuit. So another key point I'd like to mention as well is these wires, there we go, have no resistance. They're perfect. Do they exist in real life? Of course not. This is just a representation of a circuit. So we get perfect wires, and the only thing that becomes important is the load itself, which in this case is a 5 ohm resistor. Now, a couple more things. This circuit is exactly the same as these circuits. These circuits are all three of them are exactly the same. Alright, well, assuming they're 5 ohm resistors, which I haven't labelled. There we go. So all 3 of these circuits are exactly the same. There's a couple of things I'd like to run through. So all of this voltage that we see here, the voltage being supplied to the circuit, is utilised pushing charge through this resistor. So if I measured the voltage across my 5 ohm resistor, I would measure 10 volts across that one resistor. So what is voltage? Very quickly talk about that. Well, the voltage is the energy provided per coulomb, if you like, per unit charge, to move the charge through the circuit. So it's the energy provided per coulomb to move the charge through the circuit. And it's got units. 1 volt equals 1 joule per coulomb. So the voltage only exists to do one thing, and that's to move charge through the circuit. So in the circuit that we have, on the left hand side there, you can see we've got 10 volts pushing charge through a circuit, and all of those 10 volts are utilised across that 5 ohm resistor. Now, if I take that 5 ohm resistor and change it, let's say make it a 500 ohm resistor, then it's still going to have 10 volts across it because that's where the voltage goes. It goes where it's needed to move the charge through the circuit. Now I can make it 5,000 ohms, 5 million ohms, 0.5 ohms, a millionth of an ohm. It doesn't matter. That 10 volts only has one job, that's to move charge through that circuit, and the only obstacle is the resistor. So all of that 10 volts will go across that resistor regardless of the value that it has. The only thing that changes is the amount of effort it takes per unit charge. So the amount of effort it takes to move the charge through. So 10 volts can move a big charge through a small resistance, or a small charge through a big resistance. And that's all controlled by our little equation V equals IR. So I can find how much charge is being moved through per second by rearranging that equation, by taking my V equals IR and rearranging it for current. So I can put it in my triangle if I want, V equals I times R. IR, I can rearrange that, of course, by covering over I to get a value for the current, and current equals voltage divided by resistance. So as the resistance increases, the current decreases. But all of the voltage will be across that one resistor. Okay, so let's look at a slightly different scenario. So let's look at a situation where I have 2 resistors in the circuit. I've still got 10 volt power supply, I've got 2 resistors in the circuit, and let's give them values. Say 4 ohms and 6 ohms. So what do we want to know? We probably want to know what the voltage is through each of the individual resistors. We probably want to know what the current is in the circuit. There's a few different ways of going about that. So let's have a look. First things first, we can calculate the voltage across the individual resistors in one of two ways. We can add the values of the resistance together to reduce the circuit to make it just a very basic circuit, and we can calculate the current that way. And of course that's straightforward to do, because here we've got resistors in series, and for resistors in series the total resistance is just equal to R1 plus R2 plus R3 plus however many there are in the circuit. So in this case it's just 4 ohms plus 6 ohms, which is 10 ohms. So if I was to look at a circuit in its most basic form, it's the equivalent of this, and of course we've got a 10 volt power supply. Now straight away we can use our V equals IR equation. We can find the current by doing V divided by R, and the current in the circuit is in fact given as 10 volts divided by 10 ohms, which is 1 amp. So that tells me that in my circuit I have a 1 amp current moving around the circuit, and that's the same in both of them. Okay, so I can use that, and I can use my equation again, V equals I times R, and I can use that to calculate the value of the voltage across each of the resistors. Because if I look at my circuit on the right, then I know that my 10 volts is the value of the voltage across the entire resistance. But what happens for the individual resistors? Well, okay, I've got V equals IR, and let's look at the first one. I have a current of 1 amp times 4 ohm resistance. That gives me a value of 4 volts. If I look at my second resistor in the circuit, then again V equals IR, that's going to be given by 1 amp times 6 ohms, which gives me a value of 6 volts. So I can break it down. Immediately I have 4 volts here, and I have 6 volts here. There we are. That's one way that we can do it. I've got the current, I've got the resistance, and from that I can calculate the voltage across the individual resistors. There's another way I can do it, so let's have a look at that. Now, the second way that I can calculate the voltage across the individual resistors is to do it as a ratio. And there's a little equation that we use. It's the voltage across the resistance is given by the supply voltage multiplied by the resistance divided by the total resistance. There we are. And if anyone's wondering how I remember that, it's just, well, one of the memory aids I have. Very visible rust over all robots. Now, let's put that into practice and work through it. If everything goes well, then I should get exactly the same answers that I just got the other way. Okay, so let's look at it. Suppose I'm interested in the voltage across the 4 ohm resistor. Then I take the supply voltage, 10 volts, multiplied by the 4 ohm resistor, divided by the total resistance, which is 4 ohms, plus 6 ohms. There we are. And that will get me a value of 4 volts. So exactly the same value. There we go. Excellent. 4 volts across here. And if I want to find the voltage across the 6 ohm resistor, I do exactly the same way. Supply voltage multiplied by the 6 ohm resistance divided by the total resistance, 4 ohms plus 6 ohms, and that gives me a value of 6 volts. There we are. So exactly the same thing, regardless of how I do it. Now suppose I want to calculate the value of the current in the individual resistors. Alright, let's have a look at that. I can use my V equals IR, so I equals V over R. So let's look at it one at a time. The current in my 4 ohm resistor, that's going to be given by 4 volts divided by 4 ohms, which is 1 amp. And the current in my 6 ohm resistor will be given by 6 volts divided by 6 ohms, which is 1 amp. So however I go about doing it, I get the same answer. There's a key point I want to bring in here. This is very important. The current at this point in the circuit is the same as the current at this point in the circuit is the same as the current at this point in the circuit. So the current inside my 4 ohm resistance is the same as the current inside my 6 ohm resistance. It doesn't change. So 1 amp, 1 amp, 1 amp, regardless of where I am in the circuit. So that's one of my key rules. Let's put that down. The current at the start equals the current in the middle equals the current at the end. It doesn't change. If the circuit splits up into different sections, the current at the start, you might end up with a lot of different roots in the middle. You'd add all the currents together. It will still end up with the same value. Current at the start equals current in the middle equals current at the end. So let's start having a look, just a little bit, nice and quickly, at parallel circuits. Alright, so this circuit's just the same as having two separate circuits jammed together. What do I mean by that? Well, if I take one of these components and break it, the other one will continue to work, business as usual. Okay, so let's look a little bit more at the voltage and current in this section. Let's give these values. Let's give this 4 ohms and 6 ohms. Why not? 4 ohms, 6 ohms, and we'll go for our value up here of 10 volts. Okay, so each one of these circuits has 10 volts across them. We've got the maximum available voltage. 10 volts down here. So they've both got the maximum 10 volts across them. Let's get rid of that. The diagram's getting a little bit too much writing on it. There we are. Try and keep it nice and clear. Okay, so what about current? As I said, we've got current at the start equals current in the middle equals current at the end. So we've got current here, we'll call it I1. Current at the start, I1. Current in the middle, I2. So here we go. This current plus this current. And at the end we have I3. Current at the start equals current in the middle equals current at the end. Alright, so now what I'm going to do, I'm going to calculate out the value of the currents in the middle. So here we go. We have our V equals IR. And of course that changes into I equals V over R. And each one of these resistances has the maximum voltage. They've both got 10 volts across them. So let's look at the current through our 4 ohm resistor. That's 10 volts divided by 4 ohms. That gives us 2.5 amps. Now if I look at the second one, so let's try and label this in actually, 2.5 amps. If I look at the 6 ohm resistor, then again the current equals voltage over resistance, which is then 10 volts divided by 6 ohms, which is 1.67, so yeah, 1.67 amps here in the second part of the circuit, 0.67 amps. Okay, so that means that I2, the total current in the middle, is 2.5 amps plus 1.67 amps, which gives us a value of 4.17 amps. Okay, so now what we're going to do is we're going to take that circuit and we're going to reduce it slightly. Because whenever we're dealing with these things, it's always a good idea to be able to reduce it to the most basic circuit that we have. The most basic circuit we have in this case is just one resistor, which is, there we go, one resistor which is attached up to some power supply. In this case, of course, 10 volts. So what we want to do is take the circuit on the left, convert it into the circuit on the right, and we'll just check our values, see whether or not the values for the current are correct. Okay, let's do that now. So the first thing we need to do is find the equivalent resistance in the first circuit. And the way we do that is 1 over RT is just 1 over R1 plus 1 over R2 plus as many as happen to be in the circuit. Okay, so let's calculate that out now. That's 1 over 4 plus 1 over 6, which is 6 plus 4 divided by 24. So that's 10 over 24. So 1 over RT equals 10 over 24. Of course, this isn't what we want. We don't want 1 over RT. What we want to do is find the value of the total resistance, RT. So we take everything and we flip it upside down. RT equals 24 divided by 10, which is 2.4 ohms. Now, something which is interesting to note, what you can see straight away is that this value here for the resistance is smaller than 4 ohms and it's smaller than 6 ohms. The value of the resistance that will give you is smaller, always smaller than the smallest value of the resistance that you have in your setup. When you're dealing with resistors in parallel, the resistance always gets smaller. Right. So what I have now is a nice little setup where I've got the equivalent resistance. In fact, what that means, if I come back up here, is that this circuit is the equivalent. I can replace the circuit on the left with the two resistances with one circuit on the right, and I'll have exactly the same effect. So let's take that and we'll look at the current inside it. Okay, so straight away we can use V equals IR. We can rearrange that to get current as voltage divided by resistance, which in this case is 10 volts divided by 2.4 ohms. And if we put that in through the calculator, we get 4.17. Oh, 16666, continuing, so 4.17 amps. There we are. So we get 4.17 amps here. We get 4.17 here. And in our center section we get 4.17. Let's come back up. So if we look at our circuit, we've got 4.17 amps, 4.17 amps. And in the center section we have 2.5 amps and 1.67 amps, which is 4.17 amps. So the current is the same in the middle as it is at the start, as it is at the end. And for the middle, what I'm saying is for this middle section, we're adding all the sections in the middle together. There we are. Let's just shade it all in. All that section together is the middle. Okay, so the current doesn't change. The current at the start is the same as the current in the middle, is the same as the current at the end, and it doesn't matter what you do to that circuit, that current will remain the same at the start, in the middle, at the end. The only way to change the current will be to change the resistance, and then it will change everywhere throughout the circuit, not just at one point. Okay, so one of the things I think would be quite useful, I think, just to get our heads around, is this idea that if we have resistors, in fact what we'll do is just put a bunch of resistors, say, of exactly the same type in parallel. There we go. So the more resistors I add in parallel, the smaller the total resistance becomes. So as the number of resistors increases, the total resistance decreases. So every resistor I add in parallel makes the total resistance smaller. And what that means is if I was measuring the current in some way, let's do that now. There we go. So what I would find is every time I add an extra resistor into my little setup here, the total resistance decreases, which means the amount of current increases. And of course a good way to think of that is just that the current here, the current at the start, I1, is equal to the current at the current at the end, I3, which is equal to, call it IA plus IB plus IC plus ID plus IE plus IF if I keep going. So every time I add an extra resistor, what happens? The total resistance goes down, but also I've got one more little bit of current to add to the total current going round the circuit. So if I put in another resistance, what's going to happen? Well, the current overall increases. The total resistance goes down. It doesn't even have to be the same resistor. I could put in a huge resistor or a tiny resistor. Each of them will have the effect of adding a little bit more current to our system. F, I, G, there we go. Now, in real life, of course, there'll be limitations on this, but this isn't real life. This is a circuit diagram. And the wires have no resistance. All we're dealing with are these extra currents that are being generated. And each one of these circuit components has the maximum voltage across them. Each one of them will have this voltage V across them. Okay, there are other ways to measure current. Now, I just want to say this now because of the exam question I'm going to go through. Another way I could measure the current is like this. I could put in a bulb. If I put in a bulb, then as the number of resistors increases, as the number of resistors in parallel increases, resistance, total resistance decreases, current, here we go, I'll just do an I, current increases, and that means that the bulb has got more current flowing through it. It becomes brighter. There we are. And one other thing I want to just discuss is this idea here. Suppose I have this voltage. Let's give it 20 volts, why not? And I have a bunch of circuit components. Here we go, I've got a resistor, I've got a bulb. Doesn't really matter what I have in there. I attach it up to a bike, why not? Little handlebars, seat, it conducts electricity, doesn't matter. In fact, what I would do, of course, in real life I wouldn't use a bike, I would use a resistance to show that I've connected it up to the metal frame of a bike. There we go. So another the resistor. That's it. So I've got 20 volts here. Each one of these has a voltage across it. V1, V2, V3. One other key point that's very important is that if I add all these resistances together, voltage 1 plus voltage 2 plus voltage 3 plus whatever I put in, I can connect it up through a ham sandwich. I can connect it up through, let's see, what else do we have? A thermistor or a light dependent resistor or any of those things. Then all those little individual voltages that I add together will give me 20 volts, because the 20 volts goes where it's needed. This is what I have, and this is what will be used to push current through the circuit. So this is what's going to be V1 plus V2 plus V3 will give me 20 volts. If I change it to 40 volts, then V1 plus V2 plus V3 will give me 40 volts. Alright, so that's our key point. Let's have a little bit of a look at what happens when we mix series and parallel circuits, and then after that we're ready to tackle our question. Alright, so here we've got a circuit which is series and parallel components, and the first thing that I want to do, say I want to calculate the voltage across the individual sections or the current in the individual sections. What I need to do is reduce this to a situation where what I have is just a nice, much more easy to understand circuit, a little bit like that. So a circuit where I'm dealing with components in series. So what I want to do then is to take this idea here and find out what the equivalent resistance of that section is. Okay, so let's do that now. What do I know? I know that 1 over RT equals 1 over R1 plus 1 over R2, and if it was to continue on, R plus R3 plus R4 plus R5, and that's 1 divided by 10 plus 1 divided by 10. Well, that's 2 divided by 10. So 1 over RT is 2 divided by 10. Well, this isn't the answer, because I don't want 1 divided by RT. I don't want 1 divided by the total resistance of this section. I want to know what the resistance of this section is. So, flip everything upside down. RT is then 10 divided by 2. It's 5 ohms. So my entire circuit can then be replaced. We've got 100 volt power supply, 20 ohm resistance here, and a 5 ohm resistance here. Alright, now we have this situation, we can start calculating what the voltages across the individual sections. And once I know the voltages across this middle section here, there, between here and here, once I know what the voltage is between that section, then I can calculate what the current is in the individual resistances. Alright, so let's have a look at that, and let's do that now. So the first thing I want to do then is take this circuit that I've created, this more simple circuit in the top right hand side there, and analyse that to find out what the voltage is across the individual sections of the circuit. Alright, so there's our circuit. Let's calculate what the voltage is across the individual parts, or we could calculate what the current is inside. Let's do, you know what, let's do both. We know that V equals IR. We know that I equals V over R. So the total resistance here is just 20 ohms plus 5 ohms, which is 25 ohms. There we are. Because of course it isn't in parallel at this point, it's in series. We've made it a more simple circuit. So the current in the total circuit is given by 100 volts divided by 25 ohms, which is 4 amps. 4 amps in the middle, 4 amps at the start, 4 amps at the end. Now we could use a symmetry of the situation. We could say both of them, both of the resistors we're looking at in the parallel section are 10 ohms, and we could just divide the amps in half. That would work, but let's continue on through it. So we've got a 4 amp current travelling through our circuit. There we are. Now I could then use my V equals IR to find out what the current is, or what the voltage is on the individual resistors. So voltage across resistor that's 20 ohms would be 4 amps times 20 ohms, which is 80 volts. There we are, so I'd expect to find 80 volts there, and then I could say 100 volts minus 80 volts will give me 20 volts. That would work, because of course 100 volts has to be equal to all the voltage in the circuit added together. Or I could just calculate it out. Easy, why not? 4 amps times 5 ohms. There we go. Give me a value of 20 volts. And if I take that 20 volts, add the 80 volts, and I've got 100 volts, all my voltage is accounted for. So that's one way that I could do it. There is, of course, another way that I could do it. And the other way I could do it to find the voltage across the circuit, there we are, is to use my equation, which is that the voltage across the resistor is the supply voltage multiplied by the resistor I'm interested in divided by the total resistance. Alright, so let's look at it. The voltage across the 20 ohm resistor with supply voltage 100 volts multiplied by the 20 ohm resistor divided by total resistance, which is 25 ohms, and that will give me a value of 80 volts, exactly the same. And if I want to look at my voltage for the 5 ohm resistor, then that'd be 100 volts multiplied by 5 ohms divided by the total resistance, which is 25 ohms, and that will give me a value of 20 volts, exactly the same. So I could do it either way. Alright, nice and straightforward there. So let's look at our original diagram that we had again. I'll bring that down and we'll look at it in more detail with this information that we now have. So there we are. I know that I have 80 volts across my 20 ohm section and 20 volts across my 5 ohm section, which is the two 10 ohm resistors combined. So if I write that in, 80 volts across here, there we are, and between this side of the circuit here and this side of the circuit over here, I have 20 volts. Alright, so maybe to make this a little bit more straightforward, a little bit easier, let's just redraw it to show you that this is exactly the same as this circuit here. Right, so there we go. These two circuits are exactly the same. So let's look at that. And what we can do, we can calculate the current in the individual sections. So let's look at the current through the 20 ohm part? Well, V equals IR. I equals V over R, which is then 80 volts divided by 20 ohms, which is 4 amps. Nice and straightforward, which is exactly what we expected to find. But let's look at the part on the right hand side. I have two 10 ohm resistors. Across each of them is 20 volts. So we end up with our I equals V over R. What we have in this case is 20 volts divided by 10 ohms. And that gives us a value of 2 amps. So what I have, if I look through my circuit, I have 4 amps at the start, I have 4 amps at the end. Coming through my 20 ohm resistor, I have 4 amps. And at each one of these individual parts, I have 2 amps up here and 2 amps down there, because of course I have 2 of these. So that's it, we're back to my golden rule there. We've got the current at the start equals the current in the middle equals the current at the end. Okay, in which case, I think we're actually round about ready to jump into one of our old exam papers and run through that now. Alright, so this is question 9 from CIE IGCSE Physics paper 4. This is variant 3 and this is from 2017. In summer. Okay, so question 9. A 12 volt battery is connected in series to a 24 watt lamp and to a parallel pair of identical resistors X and Y. Figure 9.1 is the circuit diagram. There we go. So a little bit in series, a little bit in parallel. The 24 watt lamp lights at normal brightness when the potential difference across it is 6 volts. The lamp is at normal brightness. Calculate the resistance of the lamp. So, let's first things first, let's put in the fact it's 6 volts. So we get 6 volts across here. And we know that the lamp is at normal brightness. We're being asked to calculate the resistance. So the best way to do that, of course, is probably just to use V equals IR. But we have a problem. We want to find the R, but we do not know the current. So for that, we need our equations for power. We know that power equals IV equals I squared R and equals V squared over R. And what we're going to do is we are going to use our equation for power. Power equals current times voltage, because we know the voltage across it and we know the value of the power. Now, let's look at this. So we've got power equals current times voltage, and we want to find the value for the current. Power equals IV, and we want current equals power over voltage. Alright, so the current then is given by 24 watts divided by 6 volts, which is 4 amps. Now I can use my other equation, V equals IR, and I want to find the resistance. So resistance equals V over I, which is then 6 volts divided by 4 amps, which is 1.5 ohms. There we go. So let's write that in, 1.5 ohms. There we go. That's our first bit done. Now B, determine the potential difference between A and B. Actually, that, now we've run through, is surprisingly easy. Why? Because overall I have 12 volts. I know that 6 volts is here. That means that the other 6 volts must be here. And then of course 6 volts plus 6 volts gives me 12 volts. All the voltage is accounted for. So if I was writing down the calculation, it's just 12 volts minus 6 volts equals 6 volts. So the voltage that supplies minus the voltage that's been accounted for gives me the stuff that's missing. 2. Calculate the combined resistance of the parallel pair of identical resistors X and Y. So what I can do, of course, I can look at it and I can say, you know what, there's 6 volts there across the lamp, and there's 6 volts on the other section, the middle section, with the 2 resistors. So they, as they've got the same voltage, must have the same resistance. If I know that this is 1.5 ohms, then I can say that the middle section over here must be 1.5 ohms. That's one way I can do it. and that's entirely legitimate. It's a 1 mark question. Let's just do it maybe using a little bit more information. We can do it that way instead. We can say, you know what, let's look at this, 1.5 ohms, 6 volts. We can use that section there, the supply voltage of 12 volts, to find the total resistance of the circuit and do it that way instead. Let's examine that. So there's 2 ways we can do it. One, we can say it's 1.5 ohms because the value of the voltage across each section is equal, so the resistance must be equal. We could do that and just write in the value of 1.5 ohms, that's fine. Let's look at the other way we can do that as well. And the other way we could do that is to say that the voltage across our bulb will be given by the supply voltage multiplied by the resistance of our bulb divided by the total resistance. So the total resistance is given by the supply voltage multiplied by the bulb's resistance divided by the voltage across the bulb, which is then, in that case, 12 volts multiplied by 1.5 ohms divided by 6 volts, which is the voltage across the bulb. There we are. And what that would do is that would give me a total resistance of 3 ohms. And if I know that the bulb has 1.5 ohms and the total resistance is 3 ohms, then the resistance of that section must be the total resistance minus the resistance of the bulb. So it would just work out to be 3 ohms minus 1.5 ohms, which would give me 1.5 ohms. So there we go. There's 2 ways you can do it. One is to realise if the voltage across each section is the same, then the resistance of each section must be the same when you're dealing with sections in series. Okay. Part 3, the resistance of X. Let's look at that. So we're being asked now about the resistance of X. What I know is the total resistance of this segment between here and here is 1.5 ohms. Okay. The resistance of X. I know that both those resistors are equal in value because that's given to me in the question. And I know when we're dealing with resistors in parallel that 1 over RT equals 1 over R1 plus 1 over R2. Now, if those resistors are parallel, then what I've really got is 1 over R plus 1 over R, and that's 2 over R. So what I've done is I've taken that equation and I've ended up with a situation where 1 over RT equals 2 over R, where R is just the resistance of X and the resistance of Y because they're equal. Now, as always, I want to find a value for RT. In this case, I actually have it already. It's this 1.5 ohms that we calculated earlier on. So RT equals R divided by 2. Alright, so let's just write that out again. 1.5 ohms equals this resistance value of X, or Y, because they're both the same, divided by 2. Well, that means the resistance value of X must be 3 ohms. There we go. Excellent. Let's move on to the next bit. Resistor X is removed from the circuit in figure 9.1. Explain why the lamp becomes dimmer. Alright, let's jump back up to that first circuit again. It's an interesting little question, this. It's got a few tricky little twists and turns in it. So, we take this. They remove resistor X. So resistor X is gone. That leaves us with resistor Y. As we talked through earlier on, for resistances in parallel, the more resistance or more different resistors you add in parallel, the lower the total resistance is and the higher the total current is. So what's actually happening here is as you remove that segment there, the resistance of this section increases. And as the resistance increases, the current through our lamp decreases. And that's our answer. So, resistor X is removed from the circuit. Explain why the lamp becomes dimmer. Well, as resistor X is removed, the total resistance increases. And as V equals IR, what that means is the current will decrease. There we are. So, as V equals IR, I equals V over R, the current in the lamp will decrease and the lamp becomes dimmer. That's it. That's our answer. And that's us run through that question. A tricky little question. The idea that we can remove a resistor and the actual resistance increases is quite a lovely little twist on the question. And now you know how to do it. Makes it easy. There we go. So, hopefully you found that useful. If you have, please feel free to like and subscribe. And, you know what? Have a great day.